So all you have to do in this case to compute the kickoff velocity of the ship, then you take a submerged section, get the center. So if this is a 15 feet, 7.5 point here, then at the center, 25 feet distance away, right there is the center of submerged sections, okay? Then you compute the kickoff velocity at that point. That's the easiest, and the result is pretty accurate. To the main direction of a kickoff is near vertical directions, okay? When you look at the free surface here, any point in free surface, then U1, U2 are identical. So it's going to be straight up, vertical direction. As the CG goes down the below, then it's going to be slightly tilt, but not much. So that's what you have to know. So very detailed. In this case, first I said at the depth of x is equal to 1 foot. 1 foot below, then 2 foot below, but you don't need that. But here showing the old exercise problem. So then compute the theta, compute the P1. This P1 is what? This is a P max here, times exponential function comes e to the minus 0.16 over this. This is to compute the pressure at the cutoff time, okay? Then you compute the P2, so you have to compare P2 with P1 plus this guy. So 575 plus 15, which is lower than minus 610. So to compute the U2, then you will use P1 plus PA plus PD, then get the result out. So PT is, total PT is 560. 560, for the absolute value is concerned, this PT is 590.6, P2 is 610, so you're going to use this right there. And then just add two parts together. So you got 6.7. So it's just all this exercise I provided here to show you how this parameter changes. So that's the only reason. But to compute the kickoff velocity of the ship, so you have to use 7.5. Why 7? X is depth is 7.5. The draft is, in this case, is 15 feet. Right at the center of submerged section is 7.5 below. And 50 feet, and the middle is 25 feet. So that's the location you will compute for kickoff velocity. Then this exercise I want you to really follow all the way through, okay? And you don't have to really worry about 1 foot below, 2 foot below, but I just compute it, okay? And kickoff velocity, how it varies along the authorship direction is in horizontal direction, but it's just an exercise, and you don't have to worry about the momentum approach. Just pick out the center of the submerged section of the ship, and compute the kickoff velocity for that point. And this is another exercise problem. I'm again assigning 2 problems today here, and of course do it after the midterm exam. Well, as you have more time, you can do as exercise. But again, due is Friday next week. And this is very interesting problem. And you have 2 medium. This media 1, and this is another media, like water, and this is oil, for example. Then shock wave comes. You can think of this as a trench or pipe, whatever. And P1, U1, you know. Input shock wave pressure. If you know P1, you know the U1. But as this guy comes, propagate, hit the interface here, then there will be the reflection wave and also transmitting wave. So here now, it generate as after hit the P1 interface, there is a reflection wave P1 prime and U1 prime, and transmitting pressure is P2 and U2. And idea is to compute the P1 prime, U1 prime, and P2 and U2. So read this, then answer the questions. This is the 3rd exercise problem, and I want to make sure you know what you're doing. So it's you had a great pleasure not solving any homework so far, but suddenly you got few problems, and 1 week, and I give you a mini project for 2 weeks. So I think it's a pretty good idea. But for last few weeks, you really enjoy the course just listening. So it's a little bit time to do some homework, okay? So I want you to take a look at. But this one, I want you to solve before Monday, because you will, in the previous midterm exam, last year's midterm exam you have, and which is very close to this problem. You will have a close problem for Monday midterm problem. So midterm last year done with a surface ship. So now this is a target point. It could be submarine down there. Then there is no such a thing as a kickoff velocity. And when the shock wave hit the target, then it will move. The question is, what's the direction of the motion for the target in the water? If it's surface ship, what happens? It's always kicking vertically. For submarine, it's not going to be vertically. Then what's the direction and what's the velocity, direction and magnitude, things like that. And my note, I guarantee, is very explanatory, and everything is all there. So if you sit down, read it, should be able to understand 100%. But if you cannot, next week, still my lab students are all there. You can discuss with them. Okay, next few pages, I put the gas bubble oscillation, recent progress for gas bubble oscillation. Couple of things I want to show you. You know, this Gears and Hunters down here, and other authors, Gear and Hunter put up the paper, which is all showing down here, which is in 2002, already 8 years ago. Look like yesterday. But his result is quite promising. As you see here, it's the first time. As you see here, look at this, the solid line there. First period, second period, third period, the gas bubble period is keep changing. It's reducing. But most important for us is the first gas bubble, the capital T. Okay? So as you look at the first gas bubble period, which is the longer in time domain, and the second gas bubble period is shorter, and third is about same, and gas bubble size is reducing. You can't keep it the same. This old investigation. So here, from this is like a radius of the gas bubble. For the second gas bubble, about roughly 1/3 is reduced, and like a third gas bubble, another 1/3 down, because its energy is keep losing, dissipate into the water. So there's sort of the magic number, about 1/3 down for the second gas bubble, size of the radius of gas bubble reduced down to about 1/3, and third bubble is about 1/3 down again from the second bubble. So that's what's happening. So this is about all I added here, because Tom Gears is a very close friend of mine, so he has done really beautiful jobs. So that's chapter 3. I'm doing a little bit pushing me to complete chapter 4. Chapter 4 is a scaling law. Scaling law, a lot of time you want to conduct the model testing rather than prototype testing, because prototype means a real ship, like a destroyer class ship, which is, I don't know how much nowadays, maybe let's say $300 million, and you put that in and put the charge, and sometimes too dangerous in terms of damage, fatal damage in the system, then you lose a lot of money. So a lot of situations to try to conduct the model testing, reduce down the model to 5 times, or reduce the model by the scale 1/10. Okay? Then conduct it's going to be cheaper, time going to be short. On the communities using it is Hopkinson's scaling. Hopkins scaling law. This is about only one we are using it in index communities. Hopkinson's scaling law. Okay, that's what I want to show you here. And first part of this chapter is dimensional analysis, basic concept of the dimensional analysis, then jump into the scaling law. Okay? And I have only 10 minutes to talk, too short, but I put the one problem to answer the Hopkinson's scaling law. And here, anyway, two parts. Have the class at 11? Raise your hand. Willie's no class today? Would you mind if I just do a little bit longer? By 15, 20? Okay? Another class is here. Then we're going to move another room across here. Maybe you record, but we'll do it as is. I really hope no other class after this, because it's term exam week, I hope. Okay, let's just go first to physical dimensions and parameter. The part of this scaling, chapter 4, the scaling, it's really dimensional analysis. Some of you took the course. When I really pick out the essence of it, why dimensional analysis? To reduce down from prototype to the model, you have to scale down. Dimensional analysis really play, which is not really applicable to index problem, but still this is really basics of home. So first, I'm going to define the physical dimensions. I want you to understand definition, because I have problem definition. Okay? Physical. For example, time, and the U.S. is here mass, but they always use as a basic quantity. They use a force. Force means multiplied by the g to the mass. Right here they use mass here. So here in my notes is a force. It's a basic quantity. Physical dimensions, okay, are the quantity which describe the states of the object, time, force, and temperature. Temperature is not the issue, okay? The surrounding environment is water. For the water, temperature is not the issue, because it's just the temperature just to relieve right away in the water, because you are dealing with the semi-infinite domain of the water, sea water, because we are dealing with a naval shock. Okay? And this the term PI generally dimensional. In other words, here's a velocity, one of the physical parameter, which has a dimensions, right? Looks like a difficult, but nothing. Okay, physical parameter, velocity, pressure, time, or decay constant, strain rate. mass density. Don't confuse it. Physical dimensions, quantity you are dealing with, the 4, including the temperature. Could say physical parameters I can say is equal to Ki. Usually this K is 1 times length to the some power, time to the some power, to the some power, P to the some power. Usually for index problem set, D is 1. Okay? All this parenthesis dimensional units of the PI. So you can compute physical parameter. So, dealing with the flat plate, which is part of section 10, easy to understand. You have an thin infinite plate, and this side is water. I'm sorry, this side is air, and this side is water. Yeah, so it's good. I should find more than a few minutes to finish this. Forgive me if you feel it's offensive. I hope it's not offensive for learning. This is infinite thin plate, and it acts as a 1. Okay, when you get into chapter 10, then I explain a lot more. But this side is air, this side is water, and underwater shock wave, plane wave is coming, then bang, hit it. Okay. Then how do you set up the equation of motion? By the Newton's second law, the mv dot, v is velocity of the plate, v dot acceleration of the plate. This is infinite, so I have to deal with the mass per unit area. Okay, this is a thin plate. Mass per unit area, so mv dot is what? Inertial force of the plate per unit area, isn't it? Just showing how do you set up the equation of motion without nothing, but just based on the physics, okay? And 2, this is the pressure, shock pressure, 2 times shock pressure, P, by multiplied by, what's the case? The pressure is a double. When this is a rigid, right? If this guy is a rigid and hit bang, what's the pressure experienced by this thin infinite plate? Twice, right? If it's rigid, twice, right? So if this is the case for rigid plate without motion. But in fact, this is a flexible plate. Whole thing is moving. It's ideal plate, okay? It's called the Taylor plate. Professor Taylor, he developed this theory. Ideal. It just has a one piece moving. Single degree of freedom system. Then it has to relieve the pressure due to the motion. If it's no motion, bang, twice of the pressure this guy experienced. But when this is in motion, rho c v much. V is the velocity of the plate. Rho c v much of the pressure has to be relieved from twice of the pressure. Make sense? due to the motion. This is what that is, rho CV. Rho C impedance, right, of the water. You know the rho C, value of the water, and twice, so this is what the equation of motion for Taylor plate. Okay, so I'm just going to use this equation to explain the dimensional analysis. How many parameters does it involve in this equation of motion? 1, 2, 3, 4, 5, 6, 7. V is already here, whether it's a V dot or V is there. 7 parameters is involved. So you have to work for 7 parameters to make a dimensionless the parameter. Then you can apply with, doesn't matter what scale, what scales you are using, 1/3, 1/5, 1/10. When you use a dimensionless parameter, then that's scale free. That's the idea. Okay? So you spend sometimes a whole semester to learn the dimensional analysis and things like that. So the 7 physical parameters you will end up using is, this is a plate mass per unit area. Is F to the first power, time, this is time to the second power, L is length to the -3rd power, Y. I just put it right here. Mass per unit area, W over G divided by A. So W is a force, G is L over T squared. A is L squared, then just to put it together is this, or you can just rewrite as this. So that's what the dimension expressed by, not the temperature. Temperature is out, D is out, F, T, and L. Okay? So that's the first step you have to make it, that V, velocity, is L over T. Then then you can use excuse me, 가셔야 돼요? Okay. Then anyway, Mr. Kim will edit that. So this L to the alpha L to the V power, alpha T to the V power, all this is, where do you see that? So that's what the physical parameters is right here. Right there. So this is where that is. This. Got it? Don't confuse not. F to the one are 0. 0 means this is 0, T to the 0 power is 1. That's what I'm doing here. So your question may be, what you want to do for? First power, T to the first power. The rho is mass density, is T to the first power f to the first power, t to the second power, L to the minus fourth power. Can you get that? You can get that. Because you know the mass density. Got it? Then C, sound velocity. So now next step is now I want to make a non-dimensional quantity. There is no time related to time, non-dimensional quantity. For example, one of the Lee, would you check whether students are out there? Nobody there, right? Okay, that's good. Then I can have a peace of mind a little bit. Sorry, I want to cover up to here today. Then you will read once again chapter 4, which is really not many pages. Then the second step is non-dimensional quantity. Now the task is to make a non-dimensional quantity, which is really scale-free. Okay? Scale-free. That's the idea. So how to make a non-dimensional quantity? For example, 7 parameters: velocity, pressures, time, all different kinds. Non-dimensional velocity. Ooh, non-dimensional velocity. That's the velocity over the v over the non-dimensional velocity is right there, right? And the time, how we're gonna use how to make a non-dimensional time. T over theta, both are time, so time over time, non-dimensional quantity, for example. But is there any systematic way to find it? Yes, there is a way. So you have 7 quantities, 7 physical parameters to work with to develop the non-dimensional quantity. So 1, 2, 3, 4, 5, 6, 7. Then lambda, I put the power. All this I don't know. You have to find out. We have to find out. And you will see in a minute here. For example, this is a non-dimensional quantity. So, for example, the time t here is in terms of the dimension. This is only capital T. You have 3 parameters to deal with. The F, the force, time t, and length L. Okay. For example, C is something like meter per second. So meter L over T. So L to the first power times T to the minus first power to the gamma, of course, gamma to the C power there. Then the idea is A is non-dimensional. Okay. In your node you have all that, right? Information there, right? Yes. Yeah. And I'm going to say that this A is F to the B1 power times L to the B2 power times T to the B3 power. To be non-dimensional, I have to set B1, B2, B3 all equal to 0. If it's not 0, then what happened? Then that's a dimensional. So you can't do that. To qualify for non-dimensional, you have to set B1, 0, B2, 0, B3, 0. Got it? So now you can put all this M, something like right now for explanatory purposes, you can, for this one, I have to put right there T to the gamma T right here. And C, you know, C is this, you have to put this guy as a part of it here. Okay? So you just stick them in the dimensional expressions all here, so you will end up having F to the some power, T to the some power, L to the some power. Then you will have, you will put all the F relevant to here, then T and L, then you have to set that equal to 0 because B1, B2, B3 are equal to 0. And let's see what I have here. So if you collect all the F terms, then in this case, it happened to be the gamma M plus gamma P plus gamma rho. Is it confusing? Nothing, not confusing. You just collect the superscript of F and the T and L, then set equal to 0. That's all I'm doing here. So then you have 3 equations set, which happen to be B1, B2, B3 equal to 0, all zeros. Then you have to solve for how many parameters? 7 parameters. Gamma, gamma M, gamma rho, gamma M here, which is same here, you don't have to worry. And gamma V here. It's all total, how many? 7 superscript. Okay? How many equations you have? You have 1, 2, 3 equations. How many unknowns? 7 unknowns. Can you solve it? Can you solve? Can you solve? 처럼? You have 3 equations and you have 7 unknowns. You cannot solve. In a sense, to have a unique solution, you cannot solve. To have a unique solution, but who cares to be a unique or not unique? That's what the dimensional analysis is for. You can solve for 7 parameters if you assume how many? 4. If you assume 4, you can get the rest of 3. Rest 3 parameters because you have 3 equations set. That solution is not the unique solution. That solution is not the only solution, but it's because it satisfies the 3 equations. It's not the unique solution. I don't need a unique solution, but I need a good solution which meet this 3 sets. Then you can get the 7 non-dimensional parameters. Then use for your apply the model testing. That's what I'm going to apply. I have Korea Institute of Machinery and Metals, and one of the directions I want to do is using exactly Taylor plate and determine the non-dimensional equations apply to any shape to check out So this is the exactly same situations. So you got the essence, what I'm trying to do, right? You pick out the 4 solution yourself, which is the unique solution. The remaining 3, then you have a 1 set of solution which meet this equation set. And you could have a many different set, but that's okay. That's perfectly fine. So here, this is what I'm doing. It's a 1, 2, 1, 2, 3, 4, pre-selected. To determine the remaining 3, and then others you all just going trivial sense for the non-dimensional parameter for P naught. You can determine this or that non-dimensional. And for rho and m, you select the 1 set, you determine the remaining set. So all this is my version of non-dimensional parameters. Hassan, you can select your own non-dimensional parameters, and then you can write using these 7 non-dimensional parameters. You write Taylor plate equation using the non-dimensional parameters, and I can write like this using the non-dimensional parameters I discovered. The set would be different, okay? If it's non-dimensional, there's important things you can claim that I show in the next line right here. Take a look at it. Like it's okay. Dimensional quantity is scale free because velocity, non-dimensional velocity, scale free. Okay, so this capital V is non-dimensional. The so is equal to non-dimensional velocity for prototype. P means, and so this is true. Then if you open the non-dimensional quantity, which is V is actual velocity in the model over C is acoustic velocity of the model. C naught is what tested in the water. Then there's a prototype. If I say this is C naught, pretty good, right? So then what? The Vm, the velocity quantity measured in model is velocity quantity in prototype. That's beautiful, isn't it? This is beautiful. But one assumption is when you conduct the model testing, you conduct the model not in the oil environment, but just the water environment, same water. Okay, same water. Then velocity quantity you measure in the model testing is same as anticipated velocity to be tested in prototype. It makes sense why trying to get the non-dimensional quantity, because this is true, nothing but true. This capital V here is a non-dimensional quantity. It's a scale free. So this is not the Taylor plate. And so, all right. So now extended. This is the 7 one-dimensional parameters. So I said it is true for any scale. Second part is assumptions. I want you to fully understand. Prototype model has to be the same material. Same material means material density, mass density has to be same. Same material means failure stress has to be the same. You can, if prototype is a steel, if the real ship, if you use the HY80 steel for your model, you cannot use aluminum. Same material, one assumption, one demand. Okay, for Hopkinson's scaling law, which is I'm explaining to you. And the lengths scale linearly. Lengths scale linearly. What does it mean? If the length of your boat is 100 meters, scale down 10, then your length in the model should be how many meters? 10 meters. You scale down by a factor of 10. Okay? Your thickness for the hull, 10 centimeters, then the hull thickness should be 1. This is the case, we said scale down to a factor of 10. Scale, yeah, really. Willie of me a little bit. Is no. Why? Why? Because in this environment, there is a quantity you can control. Only God can control. For example, this depth is related to the G, gravitational acceleration. You can't question arises, what should I then then my answer is yes. Us to keep. So with some error we have to deal with it. And the surface tension in the free water you can control. You can. And the damping, energy dissipation by the damping you can control. So we have to live with it. Okay, so That's why we have to always obey to the God. Whatever your God is. Did I answer your question? There is some difficulties, but majority are good. Okay? Stress, strain, everything can scale. Strain rate, non-dimensional already. Oh, no, I'm sorry. Strain rate is, what's the unit? 1 over second. Then we have to find the scale. Well, we will see in a minute. This is important. Atkinson's scaling. Then these two situations, same material, length scale linearly, except charge depth or target depth. Scale doesn't mean much, but I would still scale that. I would still scale that. Okay? Because there is no other approach. So, because G doesn't change, because it's deeper, then it has the higher hydrostatic head. So I would scale. Okay? I would scale. I have example problems. Same material means the density, mass density is the same, and failure stress is the same because it's the same material. Okay, now what's the whole idea? Structure immersed in a fluid is subjected to a shock wave loading imparted through the fluid. That's what that is. Experimental analysis approach. Construct a small-scale model of the structure and perform the shock response experiment in smaller scale. Why? To save time and money. To extract as much useful information as possible, as quickly as possible, with a minimum cost. That's the reason to conduct the model testing. Then some stupid guys say, is there any uniqueness doing this? Who cares whether uniqueness is there or not? I want to do a job, good job, get a good result. I don't care about the uniqueness of the solution, as long as result is good. So who cares? Okay, so approach is to pay attention here. Basic two assumptions spelled out into three. Length of the model is scale factor lambda times length in the prototype. You follow me? Right? So this lambda has to be greater than 1. Greater than 1, then what happened? Model is gonna bigger than the prototype. Nonsense. So L in model is any quantity which has a length, has a direct connection to scale factor. And this raw mass density and the failure stress are involved in the same material. So it's called invariant. So lambda to the 0 power is equal to 1. So which means mass density in the model is same as mass density in the prototype. Clear? Failure stress model is saying failure test type. You will see in the exam problem. If you don't know, then too bad. Cast this into the lambda m, length in the model is equal to lambda multiplied by L prototype. Assumption, right? Basic assumption for Hopkinson's scaling law. Now second is a failure stress in the model. This means invariant, right? Doesn't vary. The scale factor is 1 for failure stress in prototype. And as you look at this guy, as you look at this, what's the unit dimension for failure stress? Stress. Force over length square. Force in the model, length over length square. So unit, the dimension is force times length to the minus second power, right? But this is what case? Model is equal to prototype, right? So now what we know, Fm, we don't know. Lm we know. Lm is lambda Lp, right? So then Lp to the minus 2 power, this cancels up, right? So if you simplify it, F to the m, Fm is lambda square Fp. What does it mean? What does it mean here? The force in the model, if you're going to get the force in the model, you have to get the force in the prototype and multiply it by lambda square. If you measure the force quantity in the model, okay, you got this is measurement. You conduct the model test, then you can get, of course, the force quantity in the model. To get the force quantity in the prototype, then you have to do Fm divided by lambda square. Lambda, do you know lambda? Scale factor, you decide, you pick, right? Then you measure it. Then Fm divided by the lambda square gonna be unknown Fp. You can predict without really spending tremendous amount of the money to build up. You don't have to build. That's a time saving, money saving. So force lambda square, isn't it? Okay.